PE is investing heavily on research, especially market-focused R&D. PE Global Research is the first U.S. industrial lab. It began about over a century ago in Schenectady, New York, and its founding principle is to improve businesses through technology. Also, PE Global Research is one of the world's most diverse industrial labs. Currently, we have locations all over the world in 5 different countries, and we have over 3,000 technologists. Our headquarters is located in Estimator, New York, and also we have a technology center in Bangalore, India, and a technology center in Shanghai, China. Also, we have Global Research Europe in Munich, Germany, and currently we are building a 5th technology center in Brazil. Okay, next I'm going to talk about affective computing. This is the agenda of this talk. First, I will give a brief introduction to affective computing. I will explain what affective computing is and what are the possible applications of this technology. And then I will introduce several machine learning approaches for effect recognition. Effect recognition is very important in affective computing because effect recognition, also known as emotion recognition, if we cannot recognize effects or emotion reliably, we cannot make use of them to make computer serve us better. After that, I will draw a conclusion and answer your question. Okay, affective computing. The concept of affective computing was first proposed by Professor Picard from the MIT Media Lab in 1997. Broadly speaking, it is computing that relates to, arises from, or deliberately influences emotions. That's why in the literature, people also call this type of computing emotional computing. So why are we interested in emotion? This is because emotion is fundamental to human experience. It influences cognition, perception, and everyday tasks such as learning, communication, and even rational decision-making. So we think that affective computing, especially the emotions, have great potential in the next generation of human-computer interface. Because if a computer can understand human emotion and our cognitive status, it can be more adaptive to serve the user better. One goal of affective computing is to design a computer system that responds in a rational and strategic fashion to real-time changes in user effects, such as happiness, sadness, etc., and also our cognitive status, such as frustration, excited, boredom, etc., and also our motivation. And we estimate these emotions or cognitive states from various different signals like speech signal, facial expression, physiological signal, or gesture, or neurocognitive performance, etc. So there is a lot of signal sources that can be used in affective computing. Next, I'm going to introduce 3 potential applications of affective computing. I say these are potential applications because this is still a very new research area, and we see it is very promising in some applications, but currently it is still in the implementation phase. So the first one is that affective computing can be integrated into next generation call center technologies, and many of us have this experience. After we talked with customer service representative, we received another call asking us to do a survey to evaluate the performance of the agent. But with affective computing, we may be able to eliminate this time-consuming and also inconvenient process. And during the call, we can estimate in real time the emotion of the agent and also the customer from the speech signal. And after the call, we will know whether the customer is satisfied or not and how professional the agent is. And so So this will help us to automatically evaluate the agent performance. And also, through this process, we may be able to build a profile for each agent. This agent is particularly good at handling a certain type of code to deal with certain type of customer. So in this way, we can write the code better. So if we have this kind of code, this type of customer, we know to which agent this code should be forwarded. Okay, and the next potential application is to advance personalized learning. And personalized learning is identified as one of the 14 National Academy of Engineering grant challenges. It is well known in psychology that our performance in mental tasks like learning is a function of strength, also called arousal in affective computing. So, on the right-hand side of the screen, you will there is a figure which illustrates the well-known Yerkes-Dodson law, which is very well known in psychology. On the horizontal axis, you see strength, and on the vertical axis, you see performance in mental tasks. So when the strength level is low, the student may feel sleepy, and it is not good for learning. But when the strength level is very high, the student may be frustrated or very anxious. It is also not good for learning. So to optimize the performance in a learning task, we need to keep the strength at an optimal level to keep the student alert, but not to put too much pressure. So with the help of affective computing, in future personalized learning system, instruction can be individualized based on learning style, speed, interest, and emotional and cognitive state to make learning more reliable. But of course, to implement this system, we need to be able to recognize a student's emotional or cognitive state in real time during learning. Okay, the third potential application of affective computing is for the recommendation system. Recommendation systems are used to recommend information items like movies, shoes, music, books, etc. that are likely to be of interest to the user. We see lots of this kind of recommendations from many websites like Amazon. If you buy a book, Amazon will recommend you to buy the following some other books either in the same category, or other users have also bought these books altogether. So typically, a recommendation system compares a user profile to some reference characteristics and seeks to predict the rating that a user would give to an item they had not yet considered. But we can, with the help of affective computing, we can have a more personalized approach. That is, we also make use of the user's current emotional state. For example, from your computer camera or your microphone, which is recording your voice signal, we can detect the user's emotional state, and then based on your emotional state and also your other information, we can make more suitable recommendations for information items like movies, music, or shoes. Again, to implement this kind of recommendation system, we also need to be able to recognize a user's emotional state very accurately. So next, I'm going to introduce several approaches for recognizing a person's affect or emotional state. We will cover 3 pieces of research. And the first one is called subject-independent emotion estimation from a speech signal. So here we have 3 keywords. The first one is subject-independent. This means that we are going to build a system that can be applied to all users. We do not distinguish between different users. And the second keyword is emotion estimation, as I will explain in the next slide. Here we are trying to estimate emotion in a continuous space instead of categorical values like happiness, sadness, etc. And the third keyword is speech signal. That is our input signal. We want to estimate emotion from your voice. So first, let me introduce different representation of emotion. Actually, we are very familiar with the categorical representation of emotion, like happiness, sadness, anger, disgust, surprise, and fear. And these 6 emotions are called 6 physical emotions or elementary emotions. They are called physical emotions because for every person in this world, no matter where he or she is located, which language he or she speaks, he or she can always display and recognize these 6 different emotions. But emotion psychology research also shows that emotion can be represented as points in a 3D space instead of these categorical values. This 3D space is spanned by a valence, activation, also called arousal, and dominance. For valence, it ranges from negative values to positive values. Like if you are happy, you have negative valence value. But if you are very angry, your valence value will be positive. And for activation, it ranges from low to high. If one is sleepy, then the activation level is low, but one is very excited, then the activation level is high. And for dominance, it ranges from weak to strong. If the person is sad or the person is control when we are facing our boss, our dominance level may be very weak. But if we are in control of something, our dominance level would be very strong. And this dimension is usually used to distinguish between fear and anger. If the emotion is fear, then the dominance level is very weak. But if the emotion is anger, then the dominance level is strong. And these 3 dimensions are called primitive in this talk. So we already have the categorical representation of emotion. Why are we still interested in this 3D continuous representation of emotion? I think there are at least 2 benefits. The first one is that this 3D representation of emotion in terms of a continuous numerical value makes human computer interface easier to implement because computers are better at dealing with numbers. And also, sometimes we may be interested in only a subset of the primitive, like in affective gaming, where we change the game setting, like difficulty levels or background music adaptively to keep the user more engaged. We may only interested in the activation level of the user. We do not want the user to feel sleepy, but also we do not want them to feel too frustrated. And this principle also applied in the personalized learning software. So that's why we are interested in this 3D numerical representation of emotion. In the first piece of the research, I will introduce how we can estimate this 3D representation of emotion from speech signals. Let me first describe the dataset we used in this research. The dataset is called the VAM corpus, and it is spontaneous speech with authentic emotion in a German TV talk show, Viral at Noon. And this is a publicly available dataset. Currently, it consists of 947 emotional utterances from 47 speakers, 11 of them are male and 36 are female. We are interested in this dataset because it has two quite unique characteristics. First, it consists of authentic and real-life conversation. In speech emotion research, many times people use active speech. For example, we ask the actor to act a certain class, some emotion like happiness, sadness, but these may be a little different from what we we display and observe in real life. So for this dataset, we use authentic and real life conversation. It is what we can observe in real life. And also here the emotions are evaluated in the 3D space. And for most other datasets, they use categorical values, and so they become classification problem. But here we are considering it as estimation problem. And to evaluate the emotion in the 3D space is not easy. And here we use the small mannequin hue on the bottom right corner of the screen. For the first row, the faces range from happy face to angry face, and this row is used to evaluate violence. And the second row is used to evaluate arousal, and the third row is used to evaluate dominance. So we ask several audience to listen to the same utterance and to give us evaluation in the 3 dimensions. After that, we do aggregation and then to compute a final score for each dimension, for each utterance. That will serve as our ground truth, and we will design our algorithm using them as training and testing data. Once the algorithm is finalized, it will be used for any input speech signal. So to do that, we first need to extract some acoustic features. Here we have 46. We extracted 46 features, which can be partitioned into 4 classes. They are pitch features, duration features, energy features, and MFCC features. And these are quite standard features in speech emotion research, and we have features from both the time domain and the frequency domain. Of course, we can extract much more features, but that would add extra computational cost. And as we will see in the later part of this talk, these 46 features can do a very good job in estimating emotion from speech. So we think these features are enough. Okay, in this research, we used the Estimator Fusion approach for speech emotion estimation. We first designed 3 elementary estimators, which operate independently to estimate emotion in the 3D space. After that, we do aggregation to fuse the output of these 3 elementary estimators to get a final score. For these 3 elementary estimators, we have the Buster regression, support vector regression, and the local linear reconstruction. I'm not going into the details of these 3 estimators, but I would like to point out the different characteristics of them. For the Buster regression, it uses all training examples to construct a global linear regression model. For support vector regression, it selects only a subset of the training examples to construct a global nonlinear regression model. And for local linear reconstruction, it is a variant of the k-nearest neighbor method, and it constructs a local linear regression model. So if we look at these 3 elementary estimators globally, we have both global model and local model, and we have both linear model and nonlinear model. So we believe this kind of diversity can guarantee that our field performance will be better than the performance of each individual estimator. And actually, our experimental results confirm that. Okay. Here, I'm showing the 2 fusion approach used to aggregate the output from these 3 elementary estimators. So, given T estimator, we have at least 2 different approaches for fusion. The first one is called average fusion. This is also the most intuitive one. We just take the average of these 3 elementary estimators as our final output. And the second one is called locally weighted fusion. It is a more advanced approach. because usually these three elementary estimators do not perform equally well, and it is intuitive to give more weight to an estimator which performs well. And also, it is difficult to find an elementary estimator which is universally better than another one. So the estimator 1 may be particularly good at estimating low arousal emotion, and estimator 2 may be good at estimating high arousal emotion. So in this case, we want to estimate the local performance of each estimator, and then if one estimator performs particularly well in that range, we should give more weight to that estimator. So that's the basic idea of locally weighted Fusion. In this approach, for a new input, we first find in our training data set the points that are close to this new input feature, new input data set, and then we evaluate the performance of our elementary estimators using these nearest training data sets, and then we determine the weight for these estimators. If one estimator performed very well in that neighborhood, which will give it a large weight, otherwise a small weight. So locally weighted Fusion is a very adaptive way to assign weight to different estimators, and this approach was first proposed by my GE colleagues in the machine learning lab. Okay, next I'm going to show you the performance of these three elementary estimators, and also I'm using the mean absolute error as our performance measure, and we have three dimensions like balance, arousal, and dominance. So I'm showing the performance on these three dimensions. The black curve is the performance of SV support vector regression-based method we found in the literature, which used 137 featured on the same data set. And the other three dashed curves are the performance of our elementary estimators. We can observe that our three elementary estimators had comparable performance as the one in the literature, where we used much smaller. And in this figure, I'm showing you the Fusion performance by the red curve and the blue curve. The red curve is the Fusion performance of our average Fusion approach, and this blue curve is the performance of our locally weighted Fusion approach. And the other four curves are the four curves we have already seen on the previous slide. Again, we use the mean absolute error as our performance measure. So here, the smaller the MAE is, the better the performance is. So from this figure, we can observe that both Fusion approaches outperform the SVM RBF and also our three elementary estimators. And also, the locally weighted Fusion approach outperformed the average Fusion approach, and this means that it's very useful to explore local performance information. And we believe this Fusion approach is very useful in many emotion estimation problems and even general ensemble learning algorithms. Okay, for the second piece of research, I'm going to introduce a subject-dependent arousal classification problem from classification from physiological signals. This research is different from the first work and in three aspects. First, here we are interested in subject-dependent algorithm instead of subject-independent algorithm. subject-dependent means that we are going to build an algorithm. And third, here our input signals are physiological signals instead of speech signals. This is our experimental setup. We designed a virtual environment where the user is immersed in a virtual environment, and the user is driving a virtual Humvee in a desert in Iraq. During that process, we display some mental tests on the windshield, and we ask the user to indicate the right color. And we have two types of situation setting. In the first one, we call the safe setting, and where the user is focused on driving and there are no other situations. The second one is called ambush setting. When the user is driving, there are gunshots and explosions and also screams along the road, so the user is distracted. And at the same time, we ask the user to do these mental tests. So we have extra strength in the ambush setting. And in this experiment, we had three types of tests. The first one is called color naming. This is the simplest one. We just display some numbers on the windshield, and we ask the user to indicate the right color. Like for the first figure, it is red. And in the second type of test, we do word reading. So we display the name of the color, and we ask the user to indicate the right color. The third test is the most demanding one. While the user is driving in the ambush environment, we display the so-called interference or also a swoop test on the windshield. Like in the third figure, we display the word red in a blue color, and we ask the user to indicate the actual color of this figure. Like in this case, the correct answer should be blue instead of red. So this is very confusing, and we ask the user to do this in a very short period of time. So this will add an extra level of arousal or strength. So in summary, we designed the experiment to elicit three different levels of arousal, and during this process, we measure the corresponding physiological signal like a skin conductance level, respiration, EEG, and ECG. And we performed the experiment on 18 subjects, and then we analyzed the results to see if we can accurately classify these three different levels of arousal. We also use this data set to identify the optimal arousal level for each subject, but that is out of the scope of this talk. So for arousal classification, we again need to extract the features. Here there are a number of challenges in feature extraction because usually these physiological signals are very noisy, and for EEG and ECG signals, we need to do a lot of peak detection, which is also very challenging. With the help of my colleagues, we extracted 29 features shown on the right figure. Also, we invoked the machine for classification. So here I'm showing the worked machine classification results. And in this table, in the first column, I'm showing the 29 features, and in the first row, we have numbers like 1, 2, 3, 4. These are the index of these 18 different subjects, and these mark checks means which features are selected for that subject. And in the second part, we display the accuracy of SVM classification for each subject. You may observe that when each subject is considered separately, but we also tried a different experiment. We do not classify a user's arousal level using his or her own data. Instead, we try to classify a user's arousal level using other users' data. Like we want to classify the arousal level for subject 1, but we do not use his own data. We only use the data from subject 2, from subject 2 to subject 18. In this case, we obtained a very low classification rate. It was 36.9%, which is very close to random guess, because in this case we have only 3 arousal levels. To design a generic algorithm that can be applied to all users, we need to handle individual differences, which is a very well-known concept in psychology. So next, I'm going to introduce some new algorithms for handling individual differences. First, let's take a closer look at individual differences. Individual differences make it very difficult to develop a generic effect recognition algorithm with model parameters fit all subjects. We have already seen in the second experiment. Because of this, it is critical. Usually, this can be done by collecting some user-specific training data and then retuning the parameter of the effect recognition module. But because collecting such user-specific data is very time-consuming, and it may also affect the user's interest in using an effective computing system. For example, if we have effective gaming software, and before the user can start the game, if you need 1 or 2 hours to customize your emotion recognition module, then the user may lost interest in using that software. So we would like to minimize the customization effort. That is, we want to identify the optimal parameter of an model parameter. I think it's much better than 1 hour or 2 hour effort. So to handle individual differences, we make use of 2 relatively new machine learning approaches. The first one is called transfer learning. In this approach, we want to make use of the information contained in other subjects' training examples. Because although the training examples from other subjects may not be completely consistent with a new subject's profile, they still contain some useful information, but the people activate similar behaviors at the same effective state, though usually they are not exactly the same. So we conjectured that improved effect recognition performance may be obtained by combining a minimum number of user-specific training examples with a large amount of training examples from other subjects. Like in our 3-level arousal classification experiments, if we use a small number of training examples from subject 1, and we combine that training example with examples from subjects 2 to 18, maybe we can obtain better performance than using subject 1's own data. Okay, and the second machine learning approach for handling individual difference is to use active learning or active class selection, depending on the problem. But both approaches try to optimally generate the user-specific training example. If in the affective computing system, the unlabeled training examples can be generated easily, and the bottleneck is to label them then we can use active learning. But in many cases, like in the three-level arousal classification experiment, we need to know which class from which class we should generate a new example, and then we can design the experiment to generate that example. That means we need to know the class label first before we can generate the training example. So in this case, we need to use active class selection. Its principle is quite similar to active learning. I'm not going into the details of this algorithm here. I will introduce briefly how we are going to combine these two approaches to handle individual differences. So traditionally, the most intuitive method to tailor an effect recognition algorithm is to collect a batch of user-specific training examples at a time, and then we estimate the recognition performance by class validation until the class validation performance is satisfactory or the maximum number of iterations or training examples is reached. But in our proposed approach, we combine transfer learning and active class selection. In transfer learning, we also consider other subject data in internal class validation in identifying the optimal model parameter. And in active class selection, we assume that poor class accuracy is due to not having observed enough training examples. So we use internal class validation to evaluate the performance of the current estimator so that the poor class can be identified, and then we generate more training examples for that class. We tested the performance of this new algorithm on the same problem, the three-level arousal classification from experiment from physiological signals. And here are the experimental results. We have 19 small figures on this page, and for the first 18 one, each one is corresponding to a subject. The last one shows the average performance of the classifier over the 18 subjects, and we compare several different approaches, 4 different approaches, but here let's focus on 2 of them. The black solid curve shows the baseline performance, where the training examples are generated uniformly from each arousal level, and we use only user-specific data in training. And the blue dashed curve shows the performance of our newly proposed algorithm, which combines active class selection and transfer learning. In each small figure, the horizontal axis shows the number of training examples we have, and the vertical axis shows the classification accuracy. And as you can expect, generally, as the number of training examples increases, the classification accuracy also increases. But from each subject, especially from the last one, which shows the average performance over the 18 subjects, we can observe that our proposed approach, the active class selection plus transfer learning approach, outperforms the baseline approach significantly. Specific training examples, we can obtain much better classification accuracy using our proposed approach, and we can understand the benefit of this approach in another way. If given a required classification accuracy like 65%, by using our proposed approach, we only need a small number of training examples, whereas for the baseline approach, we need a much larger training data set. So it means that our proposed approach can reduce the effort for customizing an effective recognition algorithm for individual users. So this will promote the popularity career, and there are lots of challenges, lots of great applications, and also lots of fun. And if you want to learn more about Affective Computing, you can go to this website, the homemain website, which has lots of very useful information and upcoming deadlines and new publications. Okay. To learn more about GE Global Research and the exciting projects we are doing here, you are welcome to go to GE Global Research website. And also, we have presents in major social media like Twitter, YouTube, and Facebook. And also, GE is investing heavily on software, and we have lots of openings in different areas. You can find these openings and apply for them through different websites like our GE Software Center of Excellence website and also our GE Career website. And again, you can find us on Twitter and Facebook. So you are welcome to go to this website to learn more about GE and to submit your application. Okay, that's all for my talk. Thank you very much for your time, patience, and your questions and feedbacks are welcome. Thank you. Okay, we got a question here. It said, I have been increasingly interacting with Google voice search and navigation on my computer. Have they implemented algorithms like you are describing here for voice emotion recognition? What about Apple? Well, for Google, I'm not sure whether they have search algorithm using voice signal, and so far as I know, maybe they are not using this technology. But recently, I heard a talk from Microsoft Research. They said they are using a similar type of technology. For example, sometimes they want to prioritize your email message. If you are attending an important meeting and you do not want disturbance, you may want to read only the most important or most urgent email messages. So they are developing algorithms to automatically do that. So for that they need to be able to recognize effects from the email or voicemails. And I'm not sure about the Google approach, but for Apple Siri, I guess they can easily do emotion recognition from that. And I have not used the Google Siri for myself, so I'm not sure whether they are already making use of that. But it can be very easy to integrate Affective Computing technically into Siri. I hope that answers your question. Okay. Someone asked, can we use WhatsApp to learn more again? Do you mean the WhatsApp to learn more about Affective Computing? Yeah. Yeah. Here, I guess the best starting point is to go to the homemain website, which is emotionsresearch.net, and you can find all kinds of research activities and conference and publication on emotion. So the next question is, have you found your statistics to be valid across cultural boundaries? Yeah, that's a very good question. For emotion recognition, especially if we want to recognize emotion from facial expression, some people from certain countries are very good at displaying facial expression, while others are not. So sometimes your algorithm may work very well on people from a certain country, but not on people from other countries. That's why we in this talk we introduced approaches to handle individual differences and how to customize our algorithm for people from different cultural backgrounds, different countries, and also I guess to handle the cultural difference, we may need to use an ensemble approach. We should not rely on a particular only one source of input, like facial expression. We may combine facial expression, speech signal, and gesture, and also physiological signal if we can get them. And in this way, we can be more robust and accurate in emotion recognition. Yeah, so the short answer is yes, there are some cultural differences, and we need to consider that in designing a generic affective recognition software or algorithm. Thank you. So the next question is, will my computer be able to cheer me up when I'm sad? Yeah, I think in the near future we will be able to do that. Actually, there are lots of active emotional research in all over the world, especially in the Europe. People are designing affective robots or affective computers that can recognize people's emotion and then to serve people better. For computers, actually, this may be quite easy. So if from its camera or it's from microphone, it acquires the necessary signal and it detects that the user is sad, and it can automatically play a certain type of music, or in the future, if the Internet of Things becomes a reality, the computer may be able to automatically control your home setting, like a temperature, like lighting, etc., to make people feel more comfortable. And I think this can be realized in the near future. Okay, we have 10 minutes left for questions. Okay. Yeah. Okay, the next question is, what incentive will there be for the non-compliant party to agree to be scanned for emotional attributes? Yeah, this is a very good question, and I guess every affective computing-based software or application should have the option, should ask for the user's opinion before it scans the user to detect emotion. At least each such application should have the option to let the user select whether he or she is willing to be scanned to provide such input signal, like facial expression, speech, etc. Sometimes people may consider this signal as privacy. So yeah, we need to ask the user's opinion before we make use of this kind of information. But in my opinion, many people should be happy to use Affective Computing based software or application if this can be if they can provide extra convenience to them, especially if these applications do not share information with other users and do not disclose the user's private information. Okay. The next question is Sir Kim Berners-Lee doing similar emotional web research at MIT. And the user thinks this he got this information from a lecture at RPI. Well, I'm not sure about this research at MIT. The most famous research on affective computing is Professor Picardo from the Media Lab in MIT. She has a very large group, and lots of her graduates are now faculty members in many other universities. But for this professor, I'm not sure. I will check that. But I agree that emotional web is also a very good application of affective computing. Okay, I guess we are running out of time.
Dongri, thank you so much for taking the time to walk us through effective computing and the research that you've been doing and work going on here at GE. I want to thank everybody for joining our software webinar. I want to wish everyone a happy holiday season ahead, and thanks again for joining us.